Okay, this is 5.1, exponential functions. The first problem is pretty straightforward. It just wants you to evaluate f of negative 3. So f of negative 3, you can plug this into your calculator, is really 4 to the negative 3. So in your calculator, 4 raised to the negative 3, and hit enter, and it gives you this decimal, which is fine. Obviously, you can turn this into 1 over 4 to the third and represent this as a fraction. I don't know, 4 to the third in your calculator is 64. So you can write 1 over 64 as well. However you want to write it. The decimal's fine though. 0.015625. And just do the same thing for all of these. Okay, the next problem wants us to compare what they gave us, which is p equals 9 e with what we should have, which they want us to, in standard form, be p sub 0 times a to the t. Now this is exactly like I gave you y equals ab to the x. There's no difference here. They're just switching this variable and calling it p sub 0 instead of a, and they're calling this a instead of b, and this t instead of x. But this is the standard form I gave you. This is standard form as well, just with different variables. That doesn't matter. So we need to compare here. P sub 0 is what's in front here, so that's 9. That's easy. And then a is, we have to compare this number to this number, right? Because there's t, so a is this number e to the second power. And I think you can enter that in as e to the second power. Otherwise, just do that in your calculator and get the decimal either way. That'd be e to the second power is 7.389. So, okay, and this function represents exponential growth for me. And the reason why is because this number right here is bigger than 1. And we talked about whenever b is bigger than 1, it is growth. And we also talked about whenever b is between 0 and 1, a fraction, we have decay. This next one is one you're going to want to do in the calculator. It says the table below gives lead emissions in the environment in millions of metric tons from 1970 to 1992. It says t equals 0 be 1970, and so this would be 5, this would be 10, this would be 15, this would be 18, this would be 19, 20, 21, and 22, so be careful about that. We're going to enter this into our calculator under Stat, Edit. Make sure you clear your list, first, and then enter in 0 through these numbers that are up here. Go in L1, and then enter in these numbers here into L2, and then we're going to go to Stat. Now I already have some numbers in here. I'm going to pretend that these are. I'm sorry. I'll re-enter these in real quick. All right. Once you get these entered in, then we can just go to Stat, and we can go to Calculate. And we can do, they want us to do exponential, so we'll scroll down to exponential, and hit enter. And we're going to go down and hit calculate on this one, and it gives us an exponential equation that I can write down, 285.8, let me write this down right here. There you go, just copy down, put an A, rounded it, I rounded it to the hundredths here and thousandths here, but that's fine. Oh, I need to use t instead of x as well. But that's what they want us to do for that one. They want us to go back then and do stat calculate and do quartic regression, which is 4th degree polynomial. And we're actually going to store this one in vars y variable function y1. And the reason why is because it's actually this one's a better fit. As you can see, the r squared value here is very close to 1. And on our last one, stat calculate exponential regression, it was a very good fit, but it wasn't quite as good as the quartic. So hit exponential regression and hit calculate. And you'll see that it's our r squared value is 0.998. So it's a good fit, but not quite as good as the quartic one. So I'm going to go back, show you the quartic one, and then we'll write that model right here. It's a lot to write, but okay. So I copied this down just by plugging in A, B, and C here, and you get this. I don't think Webwork accepted mine, so we might have to just give you credit for this one if you can't get yours to work either. I know it's a tough one to enter in. But the fourth degree polynomial was the better fit. And then estimate in 1982. The best way to do that is in 1982, that's 12 years after we start. So what we can do in our calculator is, because I stored this in my y equals, what I can do is just go to the graph, and I can plug in 12. I can do second calculate value and plug in 12. So once we get a graph here, I changed my window to go out to the 15, and so I can see 12. And I also changed my y-axis so I could see it a little bit. But second calculate, where you go, and hit value, and then you just plug in 12, and that way the calculator will evaluate this for you. 29.963 is what I get. And that's in millions of metric tons. And so what's nice is we can see that, you know, the amount of lead that we are putting into the environment is going down exponentially starting in the year 1970, which is good news because lead's a neurotoxin and very harmful. So, but also a lesson learned, hopefully, for humans, because we don't seem to be very smart sometimes. And yeah, we can impact the environment. By putting lead into gasoline, we very much did impact the environment here in the 70s. So, good point, hopefully. All right, the next problem then, we want to rewrite this in the form a b to the t. It says right here, or I usually say a b to the x, but whatever, we have a t here now, so we're going to use a t. To do that, what we're going to do is, I can move this up. I can make this 165 times 5 to the negative t. If I want, because I know that if I move it up, the exponent equals negative. And then I can take this 5 to the negative 1, so I can write this as 165 times 5 to the negative 1 raised to the t. So I'm kind of separating that negative sign from the t. And then I'll do 165 times 1/5, so I'll change that, move that to the bottom, this 5 to the negative 1. And now I have it written in a b to the t form, where a is 165, b is 1/5. Okay, the next problem is good for determining which functions are exponential. Anytime you have the variable in the top, it's exponential. So that's going to be exponential. I don't know what these options say, but that's exponential. This is not exponential because the t is in the base. That's like a regular polynomial. This is exponential because the exponent's in the top. This is not because we have two exponents in the top. We can't have that. There's no way to combine these as like terms or anything. This one is exponential because, you know, we could rearrange this. It's really, just like we did the last problem actually. We can move this up to the top, 0.2 to the negative 1 basically to the t, and then we can rearrange this. But the exponent is still in the top, or the variable's in the top. And then in the last one, the variable is not in the top, so not exponential. Okay, another one of these problems where we want to put in a b to the x form, or a b to the t in this case, because that's our standard form when we have our initial value, our growth rate, and then our variables, t and y. So to do that, I'm going to have to simplify this. I'm going to make it 5 times 2 to the, this is t over 6 minus 1. I'm going to make this 6 over 6. And then, let's see, 5 times 2, this would be t minus 6 all over 6. And this doesn't seem to help me at all, so I'm going to go back. I'm going to go back to the first step. And I'm going to try to rewrite this. So let's see, 5 times 2 to the t over 6. Minus 1, well, I can put a 2 in the bottom in that case, because we know when we have like basis, we subtract the exponent. So I can basically just make this 2 to the 1 in the bottom, because that would get me to go back this way. If I divide like basis, I subtract the exponents. That's kind of a weird step, but I can do that. And then I can simplify this because this is just 5 over 2. Multiplication doesn't matter what order, so I'll put the 2 divided by the 5. And then I have 2 to the 1/6 raised to the t, because I can pull out that 1/6 from the t here. And now I've got an a, b to the t form. You can do this as a fraction if you wanted to, you know, but basically a is 5/2 and b is 2 to the 1/6. If you want to do this decimal, it's fine, but there's our a and b. So we start with 2.5, and our growth rate is, our growth factor is 2 to the 1/6. Okay, the next problem gives us 2 points. The point 725 right here, function notation, and the point 1331. And it wants us to write an exponential formula representing population. So in the form a b to the t. We can do this algebraically. To do it algebraically, you just plug both points in, and you get 25 in for p equals a b to the 7. and you also get 31 equals AB to the 13th. Now, this is not something I'm going to make you do algebraically because you would have to solve this system, which, I would solve one of these for A and then substitute. It's a lot of algebra, and it's, it gets a little messy, but it can be done. But you guys are more than welcome to just use your calculators on this one, do the stat, edit, and enter, and the 2 points. And then do stat, calculate, and it turns out that 10, so you hit 0 for exponential, and hit calculate, and that gives you this right here, which I've already done. And from there, you can just write this down. It's really picky, it seems to be really picky about how many decimal places it wants, so I had to use 19.4513. And then B, I had to use 1.0365. And then from there, it wants you to compare that and find out what K would be. Well, when you compare these formulas, you have 19.4513 times 1.0365 to the T, and then beneath that you have A, E to the K, T. You'll notice that if these are your formulas for P, not Y, whatever, this number has to match right there. So basically all you have to do is set E to the K equal to this 1.0365, and then, change it into log form, or take the natural log of both sides, or however you want to look at it. But natural log base E of 1.0365 gives you K. That's going from exponential form to log form, which we'll talk more about. But that's my answer for K right there. I can do it in the calculator and round it to 4 decimal places. All right, next problem is the same thing. Gives us an exponential function, base E here, and wants to write in this form. So if we compare AB to the T, we can then easily say that this B has to be equal to E to the negative 0.07. Now that's where I take the natural log of both sides or change it from exponential into log form. And what you're doing is taking the natural log of negative 0.07. That goes here, accurate to 4 decimal places. And that gives us an error because of this negative. We can't, I think I did this wrong actually. Yeah, I did change this in exponential form correctly. It's natural log base E of B equals negative 0.07. And actually, it'd probably be best for me to just do this in my calculator. I don't know what I'm thinking, sorry. Second E raised to the negative 0.07 this way. And that's just a decimal, 0.9324. Sorry about that. I didn't need to change anything. There's a number right there I can do in my calculator. Now, the tricky part then is this part down here. It says T is measured in years. Indicate whether the exponential function is growing or decaying. Find the annual and continuous rates. The rates you determine should be positive in both cases. So on our formula sheet, we have a couple formulas. We have this formula, A equals P E to the RT for continuous. And we have this formula, A equals P times 1 plus R over N raised to the NT. These are the two formulas we're going to compare to what we have here. So this one's easy because you can compare it to what we're given, and you have 150 E to the negative 0.07 T. And so you can see right away that the rate right here is right here. So that would be the continuous one would be decay because it's negative. And it's 7%. The rate is 0.07, which is 7%. And then the annual one's a little bit harder. It's annual, we're calculating 1 times per year, so N is 1. That makes it a little easier. We can compare this then to the formula that we got when we simplified and got B here. So we still start with 150, but our B now is 0.9324 raised to the T. So now we're basically just comparing this and this. And if we do that, 1 plus R equals 0.9324, we could just subtract 1, and you get R equals negative 0.0676. So that would be decay, and the rate would be 6.8% decay if we move the decimal place over to round to the 10th. I think you can do 6.76 as well, but that's decay with a 6.8%.